In popular culture, railroads are often associated with old and obsolete technology. In reality, railroads have been at the forefront of technological development throughout their history. Railroads were among the earliest business users of telegraph, telephone, radio, electronics for control, and computers. The railroad industry is important and complex. Study of the industry encompasses virtually all engineering disciplines and logistics, as well as business and personnel management practices. The various aspects of the railroad industry are so integrated that an individual specializing in any discipline will be more effective with a fundamental understanding of the other disciplines. Civil engineers must understand operation sufficiently to construct what operation needs where it is needed. Operations people must understand engineering sufficiently to know how to manage the infrastructure and how to talk to the civil engineers about effective infrastructure improvement. Rail transportation comes in many flavors: freight, long-distance passenger, high-speed passenger, high-speed freight, commuter, light rail, streetcars, and metro, subway, or elevated lines. Some lines support several of these services. Many of them have different infrastructure and vehicle requirements. However, all have the rails in common. Managing the operation of any is similar, if not exactly the same, as managing any of the others. The wheel was invented about 5,000 years ago. The wheel provided a substantial improvement over transport without, but still presented shortcomings. The application of hard wheels rolling on a hard surface drastically reduced friction. Reduced friction allowed much heavier loads to be moved by the same power. Transport was still generally confined to a single vehicle for goods and/or passengers. Wagon roads that acted as guideways appeared about 2,500 years ago. Wagon roads designed to function like a railroad were first constructed about 500 years ago. At first, slots in the plank wagon path guided the wheels. About 300 years ago, the current configuration of flanged wheels on rails was developed. A comparison of a railroad wheel and a modern rubber tire demonstrates the reason for the importance of railroads. The contact area of a railroad wheel is about the size of a dime. The contact area of a rubber tire on a small pickup truck is about the size of a dollar bill. Smaller contact area and hard surfaces introduce much less friction and resistance to movement. Less friction and resistance to movement reduce propulsion power requirements. However, friction is important to a rubber-tired vehicle. A high degree of friction is necessary to prevent undesired lateral movement. Steam engines began replacing horses as propulsion power about 210 years ago. Railroad companies as we now know them developed right after the adaptation of steam power to moving vehicles. In the ensuing years, locomotives became larger, more powerful, and faster. The size of railroad cars steadily increased, as did the number of cars that could be coupled together to be pulled by a locomotive. Increased weight and speed required the development of track technology. Today's railroad configuration is amazingly resilient, as demonstrated by these U.S. Army experiments into methods to wreck trains. However, fast and efficient rail service requires a great degree of precision in the construction and maintenance of the track. Rails were originally made of wood. Later developments included the addition of iron straps on the top of the wooden rails, iron rails, steel rails of various cross-sections and sizes, and a modern T-rail section. Research into the metallurgy that will produce the most efficient and long-lasting rails is ongoing, as is the study of the exact wheel and rail profile combination that will provide the best performance. Metallurgy research has also led to the ability to weld rail ends together. eliminating problems related to the ends of rails being bolted together. Although railroad vehicles are remarkably adaptable to track conditions, a fast and efficient railroad requires precision in the distance between the rails and the relative elevation or cross level of the rails to each other. Rails were originally laid upon and fastened to individual stone blocks. The blocks supported the rails but were not always able to maintain the correct horizontal and vertical relationship of the rails. The first solution to this problem was the use of timbers, known as ties, perpendicular to the rails. The rails are fastened to the ties at the correct horizontal separation. The vertical relationship is adjusted by adding earth, stone, or other material below an end of a tie that is too low, or removing material from under an end that is too high. This work was originally done manually. A handheld electric tamping machine used to perform these adjustments was developed 90 years ago. The foundation of the railroad has been improved through over 100 years of research and development. Various species of wood have been used for ties, each tested for longer life and resiliency than the others. Tie development has included the use of concrete, steel, plastic, fiberglass, and other materials. The roadway foundation below the ties has progressed from earth through various materials known as ballast, such as cinders and steel slag, to specific grades, shapes, and sizes of crushed stone. Research into mounting rails on continuous slabs of concrete is ongoing. Railroad track maintenance has also been the subject of extensive research and development. The first automated tamper vehicles were developed about 60 years ago. Since then, automated vehicles have been developed for every aspect of track maintenance. Automated machines can replace ties and rails, remove, clean, and replace ballast, and even replace and recompact earth below the track structure. Railroads make money by running trains. Track maintenance occupies track but does not produce revenue. So research to develop longer-lasting track structure and more efficient track maintenance machines is an important aspect of the railroad industry. The use of the track was simple in the early years of railroad development. With only one locomotive, the use of the track was not a problem. More locomotives and cars led to conflicting use of the track. Scheduling did not always work to prevent delay or collisions. Railroads became the first land transportation to need and develop instant communication. The earliest form of preventing collisions and congestion consisted of towers erected at intervals that allowed sighting by telescope of a signalman at an adjacent tower. Such signaling was replaced by various simple electronic communications devices, ranging from simple bell and switch circuits between stations with codes for the line was clear, here comes a train, etc., through Morse telegraph, telephone, and radio. Railroads are a fixed guideway system. Trains can only go where there is track. One train cannot merely move aside to allow a train to pass or move in the opposite direction. The track must be constructed in advance specifically for that purpose. Constructed track that does not meet an operating need, has the wrong configuration, or is in the wrong location is a waste of time, effort, and money. It is necessary for the trains to be at a location for overtaking or opposing movements at the appropriate time, or a delay or a collision will result. The efficiency of movement and the ability for many vehicles to be moved by a single source of propulsion power that is made possible by the rails has a cost in planning and management. It also has an infrastructure cost. The engineer of a train does not steer the train, the track does. Routing a train to another track requires a physical change to the track, known as throwing a switch. Throwing a switch is a simple matter, but involves stopping the train for a crew member to get off and line the switch for the desired route. Stopping to throw switches can be a substantial cause of delay. The first interlocking, a system that allows a single person to safely control the switches for many trains without stopping them, was patented in 1856. The first system controls were mechanically connected to the switches and signals by wires or pipes. Interlocking development has continued through mechanical, electric, electro-pneumatic, electric, electronic, and microprocessor control. Original control systems had a control range of a few hundred feet. Current systems, generally called centralized traffic control, make use of electronic technology to allow a single person to control train movements over hundreds of miles of rail line. The time-distance graph, known as a traffic diagram, string line diagram, train diagram, or just diagram, is the standard visual language of railroad operations and planning. Time is described on one axis of the graph and distance on the other. In the U.S., time is either on the y-axis, ascending upward, or on the x-axis, ascending to the right. In some countries, time is on the y-axis, ascending downward. On the highway, the driver of a commercial truck makes the routing decisions, avoids congestion, and detours around construction. Public agencies arrange road maintenance, repairs, construction, the aftermath of collisions, and snow removal. A commercial trucking dispatcher or manager has a limited view of the activity of the truck en route. On a string line diagram, a truck en route from Chicago to Denver, including everything that the dispatcher or transportation manager must consider, looks like this. That dispatcher or manager's view of the infrastructure on which the truck is moving looks like this. A railroad dispatcher or transportation manager's view of a train and all that is controlled and must be considered looks like this. That dispatcher or manager's view of the infrastructure on which the train is moving looks like this. In the past 60 years, research and development of effective methods of railway infrastructure planning has progressed from labor-intensive calculations and solutions developed on paper to sophisticated computer software for simulation of train movements and interaction. Simulation software is also developed and used for vehicle, track, signal, and power supply development and for training. The inherent efficiency of steel wheels rolling on steel rails has the consequence of very long stopping distance. At normal operating speed, stopping distance is much greater than sight distance. Operating a train is like driving a car in almost zero visibility weather conditions on an ice-covered road. The engineer's sight distance must be extended artificially for a train to operate safely at commercially viable speed. The engineer must know that the track ahead is clear for the distance required to stop at the current speed. Where the speed allowed on the track varies, such as it switches, the engineer must know in advance what the maximum speed at that location will be. Automated signal systems to prevent collisions and provide traffic control information have undergone continuous research and development for over 140 years. Braking also requires special consideration because of the low friction of steel wheels on steel rails. The original braking system consisted of switching the locomotive to reverse movement while moving forward, continuing to push backward until the train stopped. Later, mechanical brakes were added to each car. It was necessary for a train crew member to move from car to car, turning a wheel on each car to apply or release the brakes. Air brakes were invented over 140 years ago. A braking system using vacuum instead of pressurized air was developed in the same era. Vacuum brakes were common in other parts of the world but were not used extensively in North America. Vacuum brakes are less efficient than air brakes and have fallen into disuse, with limited exceptions such as South Africa. Braking systems have undergone continuous research and development since their innovation. Improvements have been made to improve application time, release time, maintenance requirements, and efficiency. Recent research has brought quick application and release through electrical controls activated by wire or radio throughout the train. Moving the train is as important as stopping it. At first glance, it appears that there are three types of locomotives: steam, obsolete; diesel, modern; and electric, modern. Actually, railroad locomotives have been under constant development for 200 years. The last of the steam locomotives, built in the 1950s, bore almost no resemblance to the first ones. Even the last of the steam locomotives contained technological advances over those constructed previously. The first internal combustion engined locomotives and self-propelled passenger cars appeared at the end of the 19th century. Advances in engine design for economy, efficiency, and low emissions, as well as increased power, have been continuous. The diesel-electric and diesel-hydraulic power transmission of modern locomotives is a relative of those in early locomotives, but are not the same beyond the fundamentals. Modern locomotives produce 40 to 80 times the power of the first ones. Among land transportation modes, railroads have the unique ability to draw propulsion power from an external source without consideration of the limitations. The first electric locomotive to take power from an external source via a contact rail as part of the track structure was introduced at the end of the 19th century. The first electric locomotive, introduced in the 1830s, however, was powered by galvanic cells. Electric locomotive technology continues to advance, with each generation of locomotive more technologically advanced than the previous. Development has come full circle with the reintroduction of battery-powered locomotives over 150 years after their original introduction. The most recent electric locomotives have over 2,000 times the power of the first one. The increasing power of electric locomotives has required the development of power distribution systems to supply them. Even the design and construction of the overhead contact wire system is under continuous study and development. Technological development is also found in operating and managing railroads. Daily operation involves thousands of employees, thousands of cars and locomotives, and hundreds of thousands of miles of track. Operating this extensive empire requires continuing development of computer systems for business information, control of the network, and training.